I guess it's about 3:05, so we'll probably get started. Will, is everything fine on your end?
Yep, we're good to go.
Okay. So all right, let me get started. Good afternoon, everyone. Thanks for coming to this next MTV Summer School lecture. My name is Chris, and I'm a PhD student working at the University of Michigan. I'm going to talk to you today about gamma ray interactions. Kind of similar to yesterday's lecture, this will touch on a lot of the fundamentals. So if you are very skilled and knowledgeable for gamma ray interactions, there may not be a lot of new information in this slide set, but of course you're welcome to stick around. If you do decide to sit this one out, that's fine with me too. So then we can get started. So I just want to start out with some applications that we use gamma ray interactions. Starting out with these more exciting applications that I think just helps us focus the conversation. So I've listed 4 pictures here that leverage these different gamma ray interactions and the different ways in which gammas interact with matter. So on the upper left, I have a picture from an industrial radiography scan. So that's computed tomography of a turbine blade. So for example, you want your turbines to be well balanced and not have any structural defects. So by using computed tomography with gamma rays, you can find if there are some cracks in the structure or any other irregularities and see inside the structure after it's been manufactured. So that can be very valuable. We're probably all very familiar with medical CT or medical X-rays. In this case, we are looking at the different mass attenuation coefficients for different types of matter. If you imagine like tissue, which might be very similar to water, and comparing that attenuation to bone or even metal, so in this case hip replacement, you'll see a very different color where someone has a metal implant. Still more medical applications would be radiation oncology, so you can use gamma rays to deposit their energy on a tumor, in this case say a lung tumor. And there's a lot of complex planning that goes into that because you do have to have that radiation pass through the human body as well. And probably the most relevant to nuclear engineers or people working detection is homeland security applications. So I showed a picture of a transmission scan of a trailer. You might use these to look for contraband, things like drugs or explosives or smuggled S&M. So it's nice to see all these pictures and applications. I've included just an overview slide just to get the discussion started as well. So we basically split up the interactions in 2 main classes, photoatomic, so that those are photons interacting with the electrons orbiting a nucleus. There are also photonuclear effects, so a photon interacting with the nucleus, and there are a few other interactions. We're going to focus today on photoatomic, so photoelectric effect, Compton scattering, and pair production. Those contribute the most to our radiation detection scenarios. They're the interactions that happen most inside our detectors. Photonuclear I'll talk briefly about, but this is more applicable for active interrogation scenarios, which we talk about in week 7. So it'll be just a short slide on that. There are other interactions we won't really talk about, things like Rayleigh scattering, Thomson scattering, Delbruck scattering. Those don't contribute much signal to our detection scenarios, but there are other modes of interaction out there. And just give you another idea about the basics, we're working on the electromagnetic spectrum, and gamma rays occur at the highest energies for these gamma rays. And they predominantly interact with atomic nuclei. So the first interaction that I mentioned was this photoelectric effect. I've shown a nice graphic over here. The main sequence is that a photon will travel to an atom and transfer its energy to an orbiting electron. In that case, it transfers all of its energy. There's no photon that exits from this reaction. It basically disappears or transfers all its energy to that electron. And that electron is then ejected from the atom with some kinetic energy. The energy is governed by the equation I included here. It's just a photon energy subtracted when you subtract the work function from that. So the energy it takes to separate that electron from the atom. I've included a few sample values in the lower right in this table. Just an important thing to see there is they're relatively small energies compared to typical gamma rays, EV as opposed to kiloelectron volts or even mega electron volts that we often work with gamma rays. You'll often see some secondary effects when there's photoelectric effect, and that's that the photoelectron leaves the atom and it leaves a vacancy. So that will result in another electron from a higher shell to fall into that vacancy, and there'll be a characteristic X-ray that's emitted thereafter. I've also included a sort of rough probability of interaction estimation. There's a lot of constants in here. You know, there's a K constant, which is tabulated elsewhere. But you can see that the photoelectric effect is sort of reliant on atomic number, Z, and energy. So does anyone have any questions about this reaction before I move on? I cannot see the chat right now, maybe because of some setting of Zoom. So maybe Will can help me out. There we go. So it looks like not many questions about this photoelectric effect. Might be good to move on. So the next interaction we often discuss is Compton scattering. This is, this starts with a photon that is going to interact with an electron. In this case, it's going to transfer some of its energy. The photon, so you could say it survives this interaction, which is in contrast to the photoelectric effect, where the electron disappears. In this case, some energy is transferred to that electron, so we call it the recoil electron, and the scattered photon travels away with some energy. And this equation describes that scattered photon energy, which is going to rely on the scattering angle, theta. Of course, there's also energy terms as well. And just to give you an idea, I've shown a plot in the lower right, which has sort of idealized energy deposition for a Compton event. So you see there's, if full energy was deposited, you have a point here, but instead there's some separation in this continuum. So if you have a scattering angle of pi, that maximizes the function. And consequently, if you have a theta of 0, that results in a very small energy deposition, the minimum. You might notice that this continuum is not a flat distribution. If it were flat, that would mean that there is a uniform likelihood of each scattering angle. But in our case, there's actually is a directional dependency. But so the question might be, how do we determine that? And that's described by this Klein-Nishina formula. So we had a question in the chat earlier about this plot, so maybe I'll spend a little extra time on it. But basically, the scattering angles for all these events are all possible, but they're not equally likely. And this polar plot should help explain that. It shows these level curves. And because it's a polar plot, the radius should be proportional to the likelihood of scattering in a specific direction. So say a 1 keV photon, if it interacts with the electron and scatters at 90 degrees, this point would be qualitatively the likelihood of that event occurring. And consequently, if you had 100 keV that interacts with the electron, scatters at 90 degrees, that'd be this point. So big thing to notice here is that these change with energy. So with low energies, you can see how it starts to get more to isotropic. As you get to higher energies, it becomes much more forward directed. So you can imagine with a 10 MeV photon trying to undergo a scatter at 180 degrees, that's relatively unlikely compared to all this forward directed. The equation I've included down here is also what can help you calculate these differential cross sections. It's a function of atomic number, Z, the radius of the electron, and also alpha, which is a proportion of the energy of the photon over the rest mass energy of an electron. So did you guys find that answer a good answer for the Klein-Nishina question in the chat, or do you have any more questions about this? Okay, just haven't heard an answer yet, so maybe it's fine. If not, just type in the chat and we can talk about it later into this lecture. Oh, suppose you define R0. I mean, it's just classical electron radius, so I'm actually not quite sure. Thinking, Will, do you have a better idea of that?
So this is taken directly from null, radiation detection and measurements, where I believe it gives you the classical electron radius. Off the top of my head, I forget the formulation.
Mm-hmm. Yeah. I apologize. I just pulled this from null, so. Michael says the plot is normalized. Yes. So it is it's a comparison, qualitative comparison of the likelihood. That makes sense, right? Mm-hmm. So if we're all good, then we can go on to the next interaction. The last of these is pair production. So this one is relatively more complicated compared to the other interactions. In this case, a photon with sufficient energy, in this case, greater than 1.022 MeV, because that is 2 times the rest mass of an electron. It's going to travel near the nucleus and will create a pair, electron and positron pair. Again, the photon disappears. And those positron and electron have an equal, or the kinetic energy is split between those particles, and it's dictated by this equation. Again, you see the energy is just the photon energy, and you subtract the rest mass energy times 2, because it needs to create that mass from the energy. This reaction generally takes place in that Coulombic field nucleus, which is why it scales with the square of the atomic number. So that gives you an idea. You might see this much more prominently in high Z materials. So this pair is created, and secondary effect-wise, the electron will travel in whatever medium it's in. The positron will also travel, but it will eventually reach another electron in the medium. And in that case, it will meet that electron and it will annihilate, creating a pair of 511 keV photons. So this is a very prominent signal you'll see if you're working with a positron source like sodium-22. You'll see a lot of 511 keV peaks. You can also see this if you're shielding very high energy photons with a high Z shield like lead. So any questions on pair production before we move on? All right. So I had listed these other interactions that were minor compared to the main 3, Rayleigh scattering, Thomson scattering, and Delbruck scattering. In the case of Rayleigh scattering, just briefly, it's a photon imparting energy on an atomic electron, but it is insufficient to ionize or excite. And this is sort of the crux here, is that if that event does occur within one of our detectors, and there's no ionization, no excitation, it's difficult for us to detect that event. In the case of Thomson scattering, it's quite similar, except it's imparting energy on the nucleus. Again, without ionization or excitation, it is difficult to detect. Delbruck follows along the same lines. This is also a very small effect that can be hard to actually see it occur. So we talked about all these different interactions, but maybe not how they interact, or how they all occur at the same time within shields or material. Just to recall that all these interactions are dependent on the energy of the incident photon and also the atomic number of whatever matter it's interacting with. So this plot, again from null, is sort of denoting where the dominant effect, or which effect is dominant for each of these domains. So for example, energy is on the x-axis, Z of the absorber or the material is on the y. You can see how dominant Compton effect is in a lot of materials. For example, when you get to very low Z materials, say like organic scintillators, some being mostly composed of carbon and hydrogen, you might find a very dominant Compton effect. And you also find for low energies, then you see photoelectric effect built in. You see pair production, how you need very high energies, and also that it doesn't just start at just above 1.022 MeV. In practicality, you might need much higher energies. To put this on more of a macro scale, I have a plot for sodium iodide. Sodium iodide is a very common scintillator, so you'll hear more about that when we talk about detectors on Friday, and also when we go into gamma detection. It's a very important scintillator, inorganic scintillator, and I've shown all these cross sections here. This is again from null. You can see, for example, this photoelectric effect, how it's relatively high at these low energy levels. You can see discontinuities associated with the edges. So K edge is when you can finally get enough energy to cause an ejection of a K shell electron. You see how Compton scattering covers a wide range of energies. You can also see pair production, how it starts again at higher energies. It becomes much more likely when you move to much higher energies. So with all this information, we can also discuss, just do an example with some simple math to elucidate these interactions. In this case, I just put a brief problem statement. Let's consider that we're working with 1.6 MeV gamma rays incident on thin gold leaf. And we measure electrons that are emerging with 0.7 MeV kinetic energy. And our job is to determine if those electrons were produced by photoelectric effect, by Compton scattering, or by pair production. Just a few assumptions we might use is, say we're working in a vacuum, so the electrons don't lose any energy as they travel to the detector. We're using a thin gold, so the electrons will not lose any energy on their way out of the gold. Or sorry, the electron will not lose any energy as it exits the gold. So we can just start with the photoelectric effect. Again, we work with that the previous equation that I had shown, and we know the energy of the electron, 0.7 MeV. We have the energy of the incident gamma ray, and we know the binding energy, which we can look up from various resources online. If we plug in those values, you do not see a match. And because this statement does not hold true, we know that the photoelectric effect did not cause this reaction. Next, we can test pair production. Again, we work from the basic equation we have. We can use kinetic energy of the electron and the positron to be the same. And we can plug in values that we know. Again, this relation does not hold up, telling us that pair production did not occur. And lastly, for this question, we test Compton scattering. So work with our basic equation again. One slight difference is that we're working with the energy of the scattered photon. So though the initial energy is 1.6 MeV, we will actually use 1.6 minus 0.7 MeV, next 0.9 MeV for this term. We can rearrange this equation to solve for the angle, and we find an angle of 41.27 degrees is what would occur, because that angle is realizable. So, and because we've ruled out the other interactions, we know that this was the effect that occurred. And you can do additional examples or tests. You can try to find the direction of the electron relative to the incident photon. That's another example we could do. I guess any other questions about this example before we move on? I think I also see a few other posts in chat that I may have to address later. I see a question from Braden. How does it impart energy without excitation if nuclei exist in discrete energy levels? Thomson scattering. Yeah, I'm not very well versed in some of these interactions because in the classes I've taken, we do not discuss like Thomson scattering in much detail. If anyone in the chat happens to know the answer to that, I'd be glad to hear. Otherwise, I can do a little more work and maybe post some notes in these slides to update them at a later time. So, any other questions about these interactions so far? I'll see Mike answered. Mike had said Compton scattering is a relativistic case of Thomson scattering. Professor Goldston says laser photons, Thomson scatter off free electrons. He agrees with Mike. Okay. Well, thanks for some of that information on these other interactions. I'll have to revise these slides to update to the Google Drive. So another example we can talk about relevant to these gamma interactions is discussing beam intensity or attenuation. These effects, photoelectric effect, Compton scattering, and pair production, are not only useful for detection, but also for shielding cases. So if we do some quick examples with this, we can use an idealized case where the intensity of a photon beam is given by this I value, the number of photons per area per unit time. And we can apply an exponential attenuation equation. This ought to be very similar to what Mike had shown at the lecture yesterday for neutrons. Again, it's exponential attenuation, so that's why the equation is so similar. And you can imagine if we have a source, we have a shield of some thickness, and we have a detector that we're going to use some math with. Whoops. So for this actual example, let's say 1 MeV gamma rays are supposed to travel our detector, and we want to use aluminum and lead to reduce the intensity to 1/10 of its initial value. So again, we can start with this exponential attenuation equation, and we can then rearrange the equation algebraically to solve for the thickness. At this point, we need to look up some data. A lot of times I use the NIST database, and I will post a link, or there is a link to this in later slides, so you guys can find that if you download the slide set. But they're often given a mu over rho, so a attenuation coefficient that is of the dimensions grams per centimeter squared. In this case, you can find the values for aluminum for 1 MeV, so these are dependent on energy. You can see how they're relatively similar, or they might be relatively similar for aluminum and lead, but because density is a factor, you can see how those densities will probably come into play. And those densities are, again, on NIST databases. And if we plug these in, so we know we want to reduce our intensity to 1/10 of its original and run through the algebra, and we get quite a difference in the required thickness. So for aluminum, almost 14 centimeters. For lead, only about 3 centimeters. And that's pretty indicative of why we often choose lead as a photon shield. Much more effective to only need a small thickness of lead versus an extremely thick aluminum shield. Again, a lot of it's due to, or the density is certainly a good factor, because a density and a high Z will contribute to a high electron density. And because these photons predominantly interact with the electrons, these high Z, high density shields make very good shields. Any questions on shielding before I move on? Okay, one minor effect to talk about shielding wise is also the buildup factor. Just to resist the temptation to use an extremely thick shield, we know that a thick shield will cause some radiation to still scatter towards a detector or a person that we're trying to shield. So this may result in detection of scattered radiation of different energies than you might expect from a bare source. And it means that our biological dose may not be reduced by the factor that we think it will. These values just appear tabulated. They're tabulated for each material, and they're a function of the energy and the thickness of the shield. I mean, energy of the photon. And you just apply it to the same exponential attenuation equation. And you imagine this calculation might get quite difficult if you have a very complex shield, or if you have a lot of geometry in your room. So a solution to get around having to do all these corrections by hand is to use Monte Carlo modeling or simulation, a code like MCMP, that will take into account all the buildup effects and any other scattering terms. I think that'll be discussed more at a later week. So any questions on that before I move on? All right. I said I'd talk briefly about some photonuclear effects. So I have a short slide here on that discusses more photofission. But in this case, we can see photons interacting with the nucleus that requires the photon to have energy beyond the separation energy for a neutron or photon from that nucleus. In general, you might say that energy is above 8 MeV. I've included a few sort of exceptions or materials of interest for this very quantity. For example, hydrogen-2, deuterium, you can separate a neutron if you have energy greater than 2.22 MeV photons. Thorium-232, you have a much higher 6.44 MeV, and even photofission of uranium-235 with a 5.31 MeV photon. These effects don't really occur in detectors, but they are very useful for active interrogation, which again, I'll be able to talk about that in week 7. Some data here that might be of interest. I have some cross sections I pulled from NDEF. Green curve is gamma fission, photofission, red, gamma 2N, and blue, gamma N. So you can see, for example, the green curve starts at about 5.1, matching our figure. You can see how they get much larger when you get to much higher energies, peaking at, say, 14 MeV about. And you can see these cross sections are in the millibarn range. If you recall from Mike's slide yesterday, some cross sections for neutrons can be quite high, say thermal neutron capture by boron or by fissile nuclei can be quite high. So you can induce these reactions usually with some X-ray generators or bremsstrahlung sources. So at University of Michigan, we have a 9 MeV LINAC, linear accelerator, that accelerates electrons up to 9 MeV, and then they'll undergo bremsstrahlung processes to produce photons up to 9 MeV in energy. And again, we'll talk about that in week 7. There's a question, how photodisintegration is different from photofission? So photodisintegration encompasses like gamma N reactions or gamma 2N reactions, where like photofission of uranium-235, we can understand that process is relatively similar to neutron-induced fission, where you get those 2 large fragments. But if you do gamma N on lead, where you're only shooting off 1 neutron as a result of that interaction, you may not really refer to that as photofission. And there's also cross sections for gamma 2N, I believe for gamma alpha particle as well. So that's all sort of subsets of that photodisintegration. All right, as I had promised, there's some resources I included in this slide set. So if you download this, you can use these links. XMUDAT, which is a program from the IAEA, which has a link there. The NIST attenuation coefficients, which I used for the shielding case. There's a lot of information there, and not only for elements, but also common compounds that you might use, or even, you can think things like water, things like that. And a lot of the plots here and equations, of course, they come from textbooks, things like Glenn Knoll's Radiation Detection Measurement book, and also the Atomic Nucleus by Evans. They're good; those are good references. So this lecture is going to start end much earlier than some of the past lectures, but here's a summary slide. Just remember, we really wanted to touch on these main 3 interactions. They're very relevant to all of our detection scenarios. I have visuals for each of these interactions. And I also include this plot just to give you an idea that you can sort of predict the dominant interactions and also illustrate how the interaction mode changes with atomic number and also with energy. So that's the last slide here. We can do some more questions as well. Just let me know. Let's see. Question about the example problem. We were able to find an angle between 0 and 180. That means it's Compton scattering. Could we rule out Compton scattering if theta was outside 0 to 180? So let me scroll back. This might be a very this is a very simple problem that I would wonder how you could make a problem such that none of these occurred and still have to be a physical process. Or you might, if you did find an angle, maybe if it fell outside the arc cosine domain, you could be sure that it was some other interaction. But because it covers from 0 to 180 degrees, I think you'll be able to find that this reaction is consistent. There's a question about buildup. There's a longer path than directed. How does energy get through? So we're working with photons, and because they are neutral particles, they will deposit this energy in these discrete interactions. So if the shield were not here, a source particle could just travel directly to the detector. In an idealized case, assume that all this space is just vacuum. So a particle born in the source with this direction just continues to travel. It is in the case when there is a shield, you would see a photon be born, it would travel to the shield, and it would undergo one of these interactions we discussed. So maybe it was a Compton scatter. It will deposit some of its energy, but that will continue to travel towards the detector. So we'll arrive certainly with less energy, but because that photon just undergoes scatters, it'll still have that same energy. James says, is there any concern with high energy electrons which are created by pair production through shielding? Yes. Although this is an electron interaction, you might find if you decided to shield a beta source, a radioactive source that emits beta particles or electrons, and you wanted to shield it with lead, you could see Bremsstrahlung radiation produced. And I think the same way with the electrons and positrons created from pair production. They'll travel in the high Z material, undergo Bremsstrahlung radiation, which basically emits photons of various energies, and those are photons again. So yeah, you can still see increases in dose from secondary photons created from those pair production electrons. Does that make sense? Braden says, angle measured is the shortest angle from the trajectory. Oh, this is for the Compton scattering. If it's greater than 180, it's just measured from the other way, so it's not greater than 180. Yes. So there's no, because of the dimensionality of the problem, yeah, you would not find 270 degrees because that would just be 90 degrees in the other direction. Does that sound good? Okay, so we said, so could we tell that a situation wasn't Compton scattering? So that'd be a question like, if I gave a different energy for that, could I give a photon and electron energy such that we'd find either Compton scattering or pair production could occur? That's certainly possible. If the rule says you can look at it from the positron for Compton scattering. Yeah. I mean, maybe if we saw that the positron creation was also satisfied, then we would know that that would be that it could be either. Okay, thanks. I can include more information, maybe a different version of that question with some more information. Yeah, I wouldn't want to give you a way to calculate this that has no way to confirm that it was not Compton scattering. That would not be a very conclusive test. So I guess if there are more questions, we can certainly answer them, but by no means do we have to go through 20 more minutes of questions. If people feel satisfied, we can certainly adjourn this session. Let's see, a couple more questions. Scattering scenarios are all possible. The likelihood changes as a function of input energy. Okay, so we can go back to the large cross-section plot. Yeah, so I mean, you can see how across all energy, there can be Compton dominance, and this plot is by no reason like it is specifically what effect is dominant. So by being in this domain where you had a 100 keV photon hitting a 100 atomic number 100, that doesn't mean that these effects will not occur. They're still possible, although it might be a bad example for the pair production. So it will change with energy. You do see Compton scattering. I think you'd be hard-pressed to find a material that has no Compton scattering. Braden asked, will iterative buildup calculation be covered in the MTV lectures? From my memory, we don't have a specific shielding lecture. So I don't think that'll be really discussed. I guess the main thing is if you did want to do a very complex buildup calculation, you'd be better off doing a simulation. Again, I imagine you just apply additional buildup factors or do some, or it'd be iterative, like you said, like find the dose or intensity after it leaves layer 1 of the shield, after you apply that buildup factor, and maybe add the second shield in to iterate. Just make sure you take that distance into account. Yeah, I could post my email address for question or comment. Yes, that's a good recommendation. Let me type it in the chat here. So I just put my email address in. I can add it to this slide set as well on the front. So if you download the slide set, you'll have that contact information. Let me know if you have more questions. I can try to get them answered. I'm not always not a domain expert for some of those more exotic interactions, so I can always get in touch with someone who is more knowledgeable as well. So try to get you the answers you need. Yeah, thanks for attending the lecture. You can also email me with feedback as well.